Okay, everybody, welcome to tea time. Have a seat. Oh, it's great to be here trying to figure out intelligence. Every little bit of it, little mysteries of little quirky things, and then we can figure out something that makes a big difference. Life is great. Today we're going to hear from Kris, who's a grad student here. Yeah. You didn't even put your name up. Oh, there's your name. I thought that was the name of the penguin. What's the thing with penguins, Kris? Penguins are beautiful. Okay, that's your message.
Yeah.
Take it away.
You're probably going to see a lot of it here.
Thank you, Kris.
Yeah. Okay, so I'm Kris, and I'm going to be talking about Finite-Horizon TD methods. And to give a quick overview of this, I'm just going to quickly summarize what TD learning is, and then I'll just start rambling about the finite horizon setting of this. So TD methods are applied in a reinforcement learning setting where you've got some agent in some state, and it has some actions available, and taking an action will give it some reward and lead it to a new state. And it chooses its actions in a state according to a policy, where in some state, it gives some probability distribution over actions, and it's not really concerned with immediate rewards, but rather it cares about returns, which are defined to be this discounted sum of rewards. And this discount rate gamma is used to specify the agent's horizon of interest, where if it's set to 0, it only cares about the immediate reward. But if it approaches 1, you care about all of the rewards. And in particular, the agent wants to know what the expected return is as a consequence of its actions. So it wants to know the expected return under its policy. And it does so by defining these value functions, where the state value function is the expected return under a policy given some state, and the action value function is the same expectation but conditioned on action 2. And so TD learning approaches this problem by trying to estimate these value functions. And so if you have some penguin in some state, it takes an action, it receives some immediate reward, and it's in a new state. In that new state, it tries to guess what the rest of this return will be. And it does so by querying its value function for that next state, because the value function is defined to be this expected return in some state. And so if it were to add up this reward it saw along with its guess, it gives it a guess for the previous state's value, and so it can update that state's value towards it. And to put it more formally, it would compute this TD target, which is the reward plus a discounted value of the next state, and it would take a step in that direction with some step size alpha. And some notes about this is that it can be applied to any signal of interest, not just rewards, and that lets you learn these generalized value functions and understand how state features work. And something that I want to emphasize in this talk is that the value function update target depends on itself. And something nice about this recursive property is that it can learn independent of span. So no matter what you set this horizon of interest to, whatever you set the discount rate to, it has a constant number of computation per time step. So the computation doesn't scale with that. But because it's trying to satisfy itself through this recursive relationship, it can lead to divergence in certain scenarios. So that's TD learning, and to introduce the finite horizon setting, we can pretend we have this infinite sum of rewards or some arbitrarily long one, and it's undiscounted. And what if we just threw those ones away, and we only cared about, let's say, the next 5 steps? So this is a case of time-dependent discounting, because you can imagine that the discount rate is set to 1 for the first 4 steps, and then on the 5th step it's set to 0, which cuts the rest of the return off. And this is independent of state transition or where you end up. It's purely based on time. And something that I should acknowledge is that episodic problems can also produce finite horizon returns, but this horizon depends on the environment, and it can still be infinite if you have some policy that's avoiding terminal states. So I still consider a return up until the very end of an episode to be an infinite horizon setting, because it's not limiting itself. It could go on to infinity in certain scenarios. So to define finite horizon returns, it looks similar, except the return is only considered up to h steps into the future. And similarly, we have value functions, which are expectations of this finite horizon return conditioned on the same things as in the infinite horizon setting. So say we want to use TD to try and approximate these value functions. So we have a similar setup where the penguin takes an action, it receives a reward, and it's in another state. And let's say it only cares about what happens 3 steps from now. So if it has 1 reward, if it wants to know what happens in 3 steps, it has to guess what the next 2 rewards will be. And one way it can do that is if it had the 2-step value function for the next state. So if it adds this guess to the previous, or to the reward it saw, it would have an estimate for 3 steps from the previous state. And so it can make an update in that direction. So an implication of this is that you have to learn multiple value functions So you have to do this for each h from 1 to some final horizon you care about. And you update a TD target, which looks similar to the infinite horizon case, except you're bootstrapping off of the previous horizon. And you do this again for each h. And also for each h, you would perform a TD update, which also looks similar to the infinite horizon case. And something important to note is that the value of the 0th horizon is always 0 because nothing happens in 0 steps. And so you can do this. You can use TD to estimate these finite horizon returns. Like, you can learn them online and incrementally. But like, this idea isn't new, that you can do this with TD. Like, it turns out that there's a paper from 30 years ago that has a section about predicting over a fixed interval, which describes this whole process of like finite horizon TD, where it says if you want to predict what happens 7 days from now, you need to know what happens 6 days from now, 5 days from now, all the way down to 1 day from now. But as far as I can tell, like, this wasn't really tried in a reinforcement learning setting. Maybe it was people didn't really think about the motivation behind it or why you would ever want to do this. So hopefully this talk is going to try and motivate why this is interesting and why you might want to do this. So 2 days ago, we saw some reasons why you might want to do this. And it was in terms of a metric, this mismatch between your performance metric, where like you measure it against a finite horizon, but it's trying to estimate this infinite thing. But it turns out, like, I didn't even think of this. Like, I wasn't thinking of it in terms of an objective. So hopefully this can bridge off of that. So one way that I view finite horizons is that it's trying to learn the step function of the return. It's applying the step function over your reward sequence, whereas discounting is applying this exponential decay over your reward sequence. And a nice thing about step functions is that you can subtract 2 step functions to get some impulse at a very specific time step. So this lets you extract individual rewards from your value functions. So if you have the sum of 10 steps and the sum of 9 steps, you can subtract them and say what the reward will be in 10 steps. And from a signal processing perspective, if you treat these as filters, the constant gamma will result in geometric weights, and that has a nonlinear phase response. So you actually distort the underlying waveform, and you lose a lot of information about how the signal actually behaves. So this might have implications in the prediction setting. And this is also a simple case of compositional GPFS, where like the answer to what happens in 8 steps depends on the answer to what happens in 7 steps, and so forth. And it gives a clear interpretable example of being able to specify a question that can leverage what has already been learned. So for example, if you already know what happens in 8 steps, you can ask a question about what happens in 9 steps and not have to start from scratch. So to address this in control, like, if you try to maximize over this fixed shorter horizon, it won't be optimal. But like, optimality isn't guaranteed anyways if we only try and approximate these values. And this can come from using function approximation, or even in the tabular setting if you're using a constant step size. And leveraging off the previous slide, like, you can still continually increase this final horizon and leverage what you already learned until you're sufficiently optimal. So something that I really like about this is that it can be viewed as unrolling TD. So this is one way to view TD, where you got some value function coming in, you add a reward to it, and you produce a new value function. And this feeds back into itself. So this can be seen as the value function is trying to satisfy itself with respect to this reward signal coming in. And finite horizon TD would look like this, where there's no more loops in it. Like, the same reward is being added at each step, but each value function is trying to satisfy itself with respect to the previous value function. And if you follow this chain of dependencies, it's unidirectional, and it eventually reaches the 0th horizon, which is always zeros. It's known from the start. It's not learned. So you get this one for free. And so because everything is grounded in the 0th horizon, it has this intuitive stability to it where it just has to work. And to further explain this, like, the first horizon is effectively learning the immediate reward, which is a stable Monte Carlo target. And so this will eventually converge if you have a fixed policy. And then the second horizon will have a stable target and eventually converge. Then the third horizon will have a stable target, and so forth. So this appears generally compatible even with nonlinear function approximation in the prediction setting, as long as you have a fixed policy. And this can also be viewed as maybe a way to bootstrap that avoids the deadly triad, because this seems generally compatible with function approximation and off-policy learning. So because I mentioned the deadly triad, I have to show you Baird's counterexample. I'm not going to really talk about how this environment works, but it has linear function approximation and it's off-policy. And it used a discount rate of 0.99, so I tried predicting up to a horizon of 100, which loosely relates to that discount rate. And I specified every horizon's weight vector to be this weight vector here, which is what was used in the book when it was talking about this divergence issue. And so I first tried finite horizon dynamic programming. I did like synchronous updating, where I swept over every state in horizon and performed all the updates synchronously. And then I tried an iterative deepening scheme where I would do some number of updates for one horizon, then move on to the next horizon, do the same number of updates, trying to simulate what happens if you kept specifying new horizons. And then I also ran one-step Finite-Horizon TD with importance sampling to see what happens in an online model-free setting without these expected updates. And importance sampling usually makes things have higher variance and even more unstable. So synchronous dynamic programming ended up looking like this, which is very concerning given everything that I've said so far. But if you let it run for a few more sweeps, it just eventually converges. And if you run Finite-Horizon TD, it also eventually converges. And this is averaged over 1,000 runs, so it's very consistently converging. There are error bars on there if you look closely enough. But the reason it looks like that at the start is because I initialized every weight vector to be exactly the same. So if like one horizon is bootstrapping off of the other value function, they have the exact same weight vector, so it looks like it's bootstrapping off of itself. But the first horizon is not bootstrapping, so that will eventually converge, and then they'll eventually cascade down to the 100th horizon where it'll eventually converge. And if you do iterative deepening, where you like slowly increase the horizon you're updating, it converges immediately. And so this, this is performing the same number of updates as the synchronous updating, but it organizes the updates in a more clever way that lets it learn a lot quicker. So maybe there's something here, but I didn't really look too far into it. So something that I've been ignoring, there's this elephant in the room, that this is not independent of span. You have to learn H value functions. And the computation scales linearly with the final horizon H. But what about if you're to do Finite-Horizon Monte Carlo? So this would have to store and sum the last H rewards. But if you only care about the final horizon and you don't care about everything that leads to it, you only have to update one value function because you have all the information you need to update the horizon of H. So under this idea where you can skip over learning value functions, we can look at n-step TD. So one-step TD looks like this, where you take one action, you receive one reward, and then you bootstrap after that. And then two-step TD takes two actions, receives two rewards, and then bootstraps. And three-step TD looks similar. And something to note is that all these value functions are the exact same value function. So because this thing is trying to estimate the thing up until the very end or something to infinity, so they're all using the same value estimate or the same value function estimate. But if we look at this in the finite horizon setting, so one-step finite horizon looks like this, where you take one action, you receive one reward, and you bootstrap off of the previous horizon. Now, if you do two-step finite horizon TD, you receive two rewards, and then you bootstrap off of the horizon that's two steps before your current horizon. And similarly, three-step finite horizon TD will bootstrap off of the horizon that's three steps before the current horizon. And the punchline of this is that you can skip over learning value functions. So you only have to learn H over n of them. And looking at this closely, you have to add up n rewards and update H over n value functions, so the computation ends up scaling with n minus 1 plus H over n.
What's n?
N is the n in n step. How many rewards you're including into your estimate. And H is the final horizon that you care about. So this has a worst case of H operations at n equals 1 and n equals H, which happen to correspond to the two extremes of one step in Monte Carlo. So if you do anything in between them, you'll save computation. And it has a best case of at n equals square root of H, which ends up scaling sublinear in span. It scales with the square root of the horizon you care about. And to give some example of this, if you use 10-step finite horizon TD to predict V100, you can store and sum the last 10 rewards, and then you only have to update 10 value functions. So that's on the order of maybe 20 operations. So the estimate for V10 would be the sum of the rewards plus 0. The estimate for V20 would be the sum of the rewards plus V10. And you can follow this up until you reach V100. And so you can improve the computation with this, and I think the square root of H is pretty reasonable, because if you're predicting like 256 steps into the future, it's on the order of maybe 16 operations. So this is all in the prediction setting so far, so now I'm gonna see what happens in control. So it's trivial to extend all of these previous ideas to learning action values in a prediction setting, but it's less trivial when you have policy improvement involved and you're trying to do control. Because there's this nuance where each horizon has to be greedy with respect to themselves. Like the best thing to do in 8 steps is 1 reward plus the best thing to do 7 steps from that point onwards. So you need to know the best thing to do for each horizon that you, for each horizon up to the horizon you care about. And because of this, the greedy action for one horizon can be different from the greedy action of from another horizon. So it's inherently off policy. So I had mixed feelings when I saw this, because it was interesting that off policiness just naturally emerged from this, but I was sad because off policiness just naturally emerged from this. So yeah, normally we treat it as 2 separate cases where we work out the on-policy case and we say it has nice guarantees, and here's the off-policy case that's not as good. So yeah. So, and also because you have to know the greedy action of every horizon, it might not be possible, well, it's not possible to get the savings from n-step methods without approximations, because you need to know what the best thing to do is at each step, and if you're skipping over value functions, you don't have the greedy action anymore, you don't have those action values to base your decisions off of. But on the other hand, like because of the unidirectional dependencies of these value functions, the optimal policy of one horizon is unaffected by the policy improvement of later horizons. So if you know the best thing to do in 2 steps, that's never going to change even if you learn what the best thing to do is in 4 steps. So in addition to leveraging like previously learned values in prediction, you can leverage previously learned policies in control. And so 1 step, Finite-Horizon QLearning looks pretty much how you'd expect it to look, where it looks like QLearning, but you're doing H value functions and you're bootstrapping off of the horizon before the one that you're trying to update. And so, yeah, again, the values of the 0th horizon are always 0. So I tried this in a tabular environment. I call it the slippery maze, and that's because for every action you take, there's a 75% chance that your action will just get overridden and it'll just take a random action instead, and the agent is unaware of this. So it's a really stochastic environment, and you receive a reward of -1 at each step. So I compared Finite-Horizon QLearning to discounted QLearning, where they were both epsilon greedy, but Finite-Horizon was epsilon greedy with respect to the final horizon it learned. And I tried those horizons, and I tried to choose the discount rates to be comparable to those finite horizons that I used there. And the main hypothesis here is that because the environment is so stochastic, even in a tabular setting with constant step sizes, it might not be worth trying to predict so far into the future because so many things could have happened and it'll just be noise after a certain point, especially with a constant step size where you're only approximating things. And so the results look like this, where if we look at the finite horizon side, if the horizon's too short, it doesn't do very well because it can't even see the goal. But if it only predicts 16 steps into the future, it ends up doing better than if it were to predict farther than that. And if we look at the discounted setting, it seems that like even though these were chosen to be similar to these finite horizons, it doesn't really have a tight connection to it, because like even though like these have like in a random walk these have the same expected length as those finite horizons, it's still including about like 30% of its mass beyond that horizon. And so like all of them perform relatively similar compared to like the discrepancies we see in the finite horizon setting, but it's further like suggests that like a shorter horizon might be better in some problems, even in a tabular setting. And so this is a very simple problem where like a finite horizon thing might look good in control, and there might be a benefit to using these shorter horizons or shorter predictions beyond like the objective you're trying to measure. But I tried this in a deep setting where I did deep multi-step finite horizon QLearning, where the way I handled the multi-step thing was to treat all of the rewards on policy and then just bootstrap off of the off-policy thing with the Q values. So I used n = 5 and predicted up to a horizon of 100, and I used the lunar lander environment. This is fully connected with one hidden layer, and all the horizons were treated as heads over this shared representation. So it wasn't that much more computationally expensive than regular DQN because they're just additional rows in some matrix. And the results look like this. And something I want to emphasize is that I didn't compare this to any other algorithm. I'm just showing one curve here. And it's because this experiment was run under certain conditions, and under those conditions, DQN just doesn't work. And so like, the first one was that this didn't use any momentum. This was just vanilla SGD. The second one was that there was no target network in this. And that's something that I intuitively would have expected because the bootstrapping targets are decoupled in time. But the real kicker that I don't understand why this is happening, and it's really bothering me, but there's no experience replay here. So like everything just worked, and it was like monotonically improving. It was pretty stable. And like I talked to Harm about this, and he suggested that maybe the problem was too simple and to try it in Atari. And right now I'm running it on Breakout, and it's only 1 million frames in, but it seems to be steadily improving, and it still doesn't have experience replay in it. And yeah, like I was expecting this to be a problem because this is a fully connected network. It's all sharing the same representation. It's all doing backprop to the same representation, but for some reason it's working. And it will probably improve if we do add these things, so that's an added bonus. So to quickly summarize, like there might be use to only considering a shorter finite horizon, because you have stable update targets. You can get an exact notion of what happens and when. It's a clear example of like, compositional GPFS, and there are a lot of empirical benefits to it. So it's no longer independent of span, but you can reduce computation and prediction with multi-step methods. And yeah, so this thing, like it's interesting because it can be applied at a fundamental level. It is well understood. It makes sense even in a tabular setting, and it seems to scale well to nonlinear cases. And so this seems to like it's opening this whole new world, or with new horizons to pursue. And like perhaps like there are better ways to handle the unavoidable off-policiness of finite horizon control. Or maybe there are better approximations for reducing computation. For example, if you had two-step actions or two-step options, like that would already half the number of horizons you have to learn. And because like you can subtract subsequent horizons to extract expected individual rewards, maybe you can learn and plan with some automatically unrolled model in time. Because learning a finite horizon return is kind of like automatically iterating a model, but instead of iterating a one-step model 10 steps, it's adding a reward at every step of that process. So it might be a bit more stable than iterating a model blindly. And maybe there's an online way to do that iterative deepening thing. It looked promising in Baird's counterexample. Maybe it could be done online in a clever way. So one way to do this is maybe each horizon can have its own step size and use some adaptive step size method like tidbit. And yeah, that's mostly what I had. Oh, okay. I didn't think I went that fast, but like, what about TD Lambda? Like I showed that like n-step methods were useful, but it turns out that with Heati Lambda, you get these truncated traces that travel through horizons. So on the left is what it normally looks like, where you have some state space and you have this decaying trace that's going through the states. But in the finite horizon setting, it looks like this, where the traces are traveling through state and time. And the problem with this is that, like, because it's a mixture of every n-step return, you need to learn all h-value functions again. So you can't really get the savings here. And I think instead it scales with h squared, so it ends up being worse than if you're to do a one-step method. But in addition to these computational savings with n-step, you also have this bias variance trade-off that you normally have in n-step TD, and here are some results in some Gridworld that show that it does what you expect it to do. So like after 20 episodes, like one step is really slow because it's really biased, and there's some intermediate end that works really well. And if you look after 200 episodes, like one step eventually wins because this is a tabular representation and it has lower variance. And this is, I guess, a video of it doing something sensible after like 1,000,000 frames, and it's still continuing to improve. And yeah, those are my extra slides. Yeah, Martha? Mm-hmm.
What happens if the horizon for the first reward you select, the sparse word problem, is beyond the horizon you chose at like 100? Are you imagining even then this will be useful because you'll generalize to someone with a UC reward, say it's earlier, or what are you imagining? That's the case that would break if you would actually have to have a long enough horizon to see that.
Like if the reward is beyond the horizon you estimated, then like I'd imagine you just can't see it. But if you look at that maze world that I use, it received a reward of -1 at each step. So I first thought that that would be a counterexample to this because everything that happens in 10 steps might always be -10, so it doesn't know what to do. But maybe just with a combination of like greedification and online learning, it kept favoring that one path, and then it just eventually still worked. But I don't know why it was supposed to work. Yeah.
Sorry if I missed this. Why was the parameter sensitivity kind of wonky for only one of the horizons? Sorry.
No problem. This one?
Yeah.
Well, in this case, like the horizon was just way too short. Because like this is the mean episode length, so it's maybe taking like hundreds of steps, and it's only predicting 8 steps into the future.
I see.
Yeah.
I got it.
So one of the things that's going on here is the cascade.
Mm-hmm.
Cascade is where you have one thing's being learned independently, and then one thing is being learned on top of that. So
Yeah.
like you have the short ones are independent of the higher ones.
Yeah.
So I wonder if you could take just that idea and separate it from the finite horizon idea. Like you could have a cascade where you're learning a fast gamma, and then also learn a longer gamma where it builds on the first part. So when you do the cascade without the finite horizon,
so that's the TD delta paper.
That's the TD delta?
Hmm. Yeah, Martha?
You can also separate to some extent in these results just by comparing it to like a finite horizon Monte Carlo strategy, which would not be TD tested. So is that worse than
Um,
like that NCT?
I saw some policy gradient methods that did finite horizon Monte Carlo, and it seemed like there was a benefit to using it. Like it was in that TD or not TD paper. Yeah.
So just a remark in terms of what kind of horizon would you use. So I would think that indeed if your sparsity of your rewards is beyond your horizon, yeah, you would probably just initially randomly walk around until your reward becomes within the visibility of your horizon. So that would be like it would do pretty poorly in those settings. But I think like we had a look at well a whole bunch of Atari games, and so we have one particular hyperparameter which was k in our case, but this also sort of gives a little bit of control over the horizon. And what we found there is that at least with Atari games, the horizon doesn't need to be that long. At least the values you use here, I think what's the longest horizon you used?
Well, in Breakout, I'm doing 256 now.
So that already seems like a pretty long horizon. And like we used a horizon, not a hard bound, but sort of a soft bound around a horizon of 100. And that across all the games seemed to work already pretty well. So I'm very curious to see like what your results are going to be at Atari, and especially if you really don't need expert replay, then that's super interesting, and would be the natural next step to look at, I think.
You mentioned that QLearning had some off-policiness and that made you happy and sad. Can you repeat that?
Okay. Well, like, it was interesting that like I wasn't really thinking of off policy yet, and was just thinking about like I guess control in general, like what the optimal objective is, and like it just like because every horizon had to be greedy with respect to themselves, like it just naturally became off policy because the best thing to do in one step isn't the same thing as the best thing to do in 10 steps necessarily, and yeah, like I thought that was really cool, but at the same time I didn't want to deal with it, but yeah, but I have to.
That lunar lander environment, how sparse is the reward in that one?
Not very sparse, but like something that I noticed, like I initially ran it with the Horizon 50, which ended up being too short for Lunar Lander, and that made it filter out certain rewards. Because like there's this cost of using fuel, but there's a worse cost if it crashes. So like when I was like just viewing the returns, it looked really bad. Like it looked like it wasn't learning at all. But when I actually like rendered it and started watching it, it was actually learning to fly really reliably. It was really stable and was just floating in the air or descending really slowly. Because in terms of the next 50 steps, the cost of fuel looks the same in every direction. So all it cares about is not crashing in 50 steps. But eventually, like after I think like 3,000 episodes just from exploration, it figured out how to get to the bottom in 50 steps, and then it eventually reached that performance.
Anyone have a last question? Patrick, I see you back there.
I got no questions. I like there's no experience replay. That's fantastic.
How about Martha? Martha was.
Yeah, but I came in like halfway through, so it was a really great talk, but I need to go back and hear what it's doing, so I'm sort of filling in what I missed, so sorry.
Okay. Thank you very much. That was a great talk.